And for people over Zoom, at any time, if you don't see the screen or if you don't hear me, feel free to unmute yourself and mention that there's a problem. Okay. All right. Wrong slide. Okay. So last class, we talked about up to the normal distribution. This is the last topic that we covered in the previous class. So yeah. Yeah, good point. Can I? Yeah, that is quite big. Can I? Like you see the four. There's like. There you go. Yeah. There you go. Thank you for letting me know. So anytime if there is anything like that, let me know. So here's the equation for the normal distribution, right? It looks quite complex, but you will see that it only has two parameters. So it's not a complex distribution at all. So it is basically in the form of e to the minus x to the power 2. So x here is our random variable, right? So x can vary, between minus infinity to infinity, right? So for the normal distribution, the value of x, first of all, is continuous. And second, x can be any number between minus infinity to infinity. Pi is a number, 2 is a number. The first parameter is sigma, and the second one is mu. So this distribution has two parameters. Yeah.
You can't see the last line, and also is the sigma in the square root?
That I may not be able to move. Can I? Because I don't see my cursor on this screen. Because I can't. I don't see the cursor. That's the issue. I think. Let me.
Sir, I know that the sigma is not under the square root.
Be okay.
If that's the question.
Yeah, I think this is better now. Thank you. So we have two parameters that we need to know, right? The first one is mu, and the second one is sigma. Mu is any number between minus infinity and infinity, and sigma is a positive number, right? So it's impossible for sigma to be negative. For this distribution, the expected value is mu, right? So if you have a normal distribution, then in average, your x is going to be mu, and your variance is sigma squared, right? So this parameter, in fact, is the standard deviation, sigma, right? Since it's a very special distribution, it has its own notation. So we denote it as n, normal distribution, with the mean of mu and variance of sigma squared. So it's like I said in the last class, it is the most important distribution that we cover in this course, not just in this course. In your life, this is the most important distribution that you will work with because it's everywhere. Okay. So just to get some idea, basically, what a normal distribution looks like. So if I have a normal distribution with mean of mu, then there is a 68% chance that that random variable is between mu minus sigma to mu plus sigma, right? So there's around 70% chance that my random variable is here, basically mu plus minus sigma. And there's a 95% chance that my random variable is between mu minus 2 sigma and plus 2 sigma. And there's a 99.7% chance, a very, very high chance, that my random variable is between mu plus minus 3 sigma, right? So if you have a normal distribution, almost certainly your random variable is between mu plus minus 3 sigma, right? Because 99.7% is a very, very large probability, right? So this is how the distribution looks like. So first, you can only focus on the blue curve. So blue curve is a distribution with mu of 0 and sigma squared of 0.2. So you can see that at 0, it has the highest value, and it's relatively packed, right? It's relatively a sharp distribution, right? Now, if I keep mu the same, but increase variance, then I have the red curve. So here you see that the maximum value is still at 0, but this is a more spread out distribution, right? And that means that, for example, for the blue curve, there's very small chance that my x is, for example, 2, right? Because at 2, my probability of the blue curve is around 0. But for the red curve, there's a much higher chance than that, my random variable is around 2. And finally, if I increase mu variance to a very large number, you see that the distribution becomes very flat, right? So in this case, I'm really unsure about my x, right? It means that my x can vary a lot in this range, right? For the third case where my variance is 5. So this is the 3 first curves show us what happens when we change the variance. Now, when we change the mu, basically the highest probability value change. So basically, this distribution shifts to the left or right in this direction, right? So my mu here is -2, and my distribution moves to here for the green curve. Any questions?
Sorry, sir. I wanted to ask you, outside of the ±3 sigma,
So
would
I
the
think there's
probability ever be? Oh, do you not hear me?
There's an issue. I hear there's a question on the. Yeah, go ahead. Can you please ask again?
Okay, I wanted to ask if outside of the range of ±3 sigma, is the probability ever exactly 0, or do we just get closer and closer to 0?
Yeah, so that's a very good question. So outside of this range, the probability is not 0, right? So in fact, the probability of the Gaussian function never touches 0. So if I go back, it is in the form of basically exponential function. So this term is basically f of x is never 0, is always more than 0. So f of x is always more than 0. It's never 0. But the limit of f of x, when x goes to infinity, that limit goes to, that limit goes to 0. So there's with the normal distribution, there's always the chance that my x is actually like very, very large number.
Okay, thank you.
Yeah. Any other questions? Okay. All right. So you might ask why, why this distribution has such a weird, function, and where is it coming from, right? And the answer is it's coming from everywhere, right? So if you start, so let me tell you one example where we arrive at the normal distribution. So this is a little bit for the future chapters, but it's important to let you know where this distribution is coming from. It's not, some function that somebody pulled out of his pocket, right? So let's look at this running example that we always have, where we roll a die, right? So if I roll a die, I know that the probability of all of the numbers from 1 to 6 is 1 divided by 6, right? So far, very easy. It's a uniform distribution, right? Now, if I roll 2 dice and I add the result, this is what the distribution looks like, right? So number 12 has a small probability because to get 12, both of the dice should be 6, right? Similarly, number 2 has a small probability because to get 2, both of them should be 1, right? But numbers in the middle are more likely, right? If you have played board games, you know that, where in the board games where you sum up the numbers around 7, like 6, 7, and 8 are very likely. They happen a lot, right? And we can see here that in this case, in fact, 7 is the most likely number, right? So this is exactly a line. Now, if I, instead of 2 dice, if I roll 3 dice and add up the result, this is how the distribution looks like, right? So for 3 dice, it already looks like the Gaussian. Oh, and by the way, we also call that, so I repeatedly called that the Gaussian distribution because it was invented, it was basically discovered by Gauss, right? So it's very commonly referred to as the Gaussian distribution or the normal distribution, right? So we can see that even after rolling 3 dice, we are arriving at a shape that looks similar to the Gaussian bell shape, right? And if I roll four dice and add the results, we see that it's becoming more and more like the bell shape. And at only 5 dice, right, when I roll 5 dice, which is not that many, it's basically virtually indistinguishable from a Gaussian function, right? And this basically plot here shows you what happens with different numbers, right? So blue here, blue distribution is the uniform curve. So the blue is right here, right? And then the second one is where I roll 2 dice. So that's the green curve, right? So that's the distribution. Here I have the yellow curve. So that's 3 dice. And the purple one looks like this. Basically, this is the purple one. So right here is the purple one, right? And in black is the actual Gaussian function, right? So you see that the purple is very, very close to the Gaussian function, right? And so one of the chapters of the book is called Central Limit Theorem. So in that chapter, we don't prove it because the proof is a bit difficult, but we basically do mention that when the number of dice is infinity, the distribution is exactly the Gaussian distribution, right? So for example, if n is like 40 or 100 for large n, the distribution is exactly Gaussian distribution, right? And what's very, very interesting and a little bit weird about this distribution is that it doesn't matter where you start from, right? So here our starting distribution was uniform, right? It doesn't need to be uniform, right? So you can have a distribution that looks like this at the beginning, like a weirdest shape you can think of, right? And you just repeat that experiment 2 times, right? When you repeat that 2 times, it becomes a little bit more like Gaussian. When you repeat that 3 times and add the results, it becomes a little bit more like Gaussian. So if you start with any distribution, right? And if you repeat that experiment n times, where n doesn't need to be large, in fact, for like 20 or 30 times. And if you average the results, so summing here, we summed the numbers. So 7 is the summation, 14 is the summation, or like 12 is the summation, 24 is the summation. Summation and averaging are very similar operations, right? In averaging, you sum and divide by the number, right? It really doesn't matter when you divide. But the idea is that if you repeat an experiment from any starting distribution, and you repeat that experiment a couple of times, by a couple, I mean like 20 or 30 or 40, and you average the results, you arrive at the Gaussian distribution, right? And that's very, very interesting and a little bit weird. So that means that no matter what's the shape of your original distribution, if you repeat an experiment enough number of times and average the results, your distribution will be Gaussian, right? So that means that you don't need to know your original distribution, right? If you're doing an experiment many times, because you always arrive at the Gaussian distribution. Any questions? Okay. So this basically central limit theorem is not something that we cover now, we cover it later. It's basically its own chapter later on. But basically this is the intuition behind. And the distribution is named after a German mathematician, one of my most favorite mathematicians. He has discovered a lot of cool things, and the Gaussian distribution is one of them. In fact, we use it a lot in my field, right? So you might think that, oh, it's like something simple that we study in an undergraduate course, but my own field is medical image analysis. So we try to improve the quality of the medical images and use AI to interpret them, right? And we constantly use the Gaussian distribution, right? So in this case, this is an original image, let's say a perfect image of MRI scan of somebody's head, right? So often, the noise is modeled with the Gaussian noise. So when you corrupt it, so this is your eye, when you add some noise, your image looks like this, right? It's like a corrupted image. I hope you can see in the projector that, yeah, it's actually, you can see that this image is noisy. And one noise that's commonly added to the images is the Gaussian noise. And then to remove the noise, basically a very powerful technique is to simply convolve this image with a Gaussian function, right? You probably have studied convolution, right? If you took signals and system, it's the same convolution. So this is convolution. So when you convolve this image with the exact same Gaussian function that we just saw, it basically cleans up the noise, right? So it's one of the basically fastest techniques to remove the noise from an image. Okay, so as I mentioned, the normal distribution has two parameters, mu and sigma, right? For the special case where mu is 0 and sigma squared is 1, we call that a standard normal random variable, right? So we add the word standard, right? So whenever I say standard, it means that the mean is 0 and the variance is 1, right? So you remember, like I did plot like a few Gaussians before. So this was like for a small sigma squared. And then when I increased sigma squared, I think the color was yellow. It became something like this. Large sigma squared, right? So when my mu is 0 and this sigma squared is 1, I call that a standard normal distribution. Sorry. And the random variable in that case is denoted as Z, right? So it's a convention that if a random variable is normal, first of all, so normal means Gaussian. So if the random variable is normal and also standard, so standard means has a mean of 0 and variance of 1, we denote that as Z, right? So we don't denote it as X or Y or something else, it's denoted as Z. And the cumulative distribution function is also denoted as phi, right? So we say phi of Z, that means probability of Z being less than or equal to Z, right? So if this is my normal distribution with some mean, actually, no, with not some mean, the mean must be 0. So this is the standard normal distribution, standard normal, right? So for the case of standard normal distribution, we know that the value of the mean is 0. So in this case, phi of Z is probability of Z less than Z. So if this is my Z, then what is phi of Z in this image? How can I calculate phi of Z? So this is my PDF. In blue, I plotted my PDF, right? How can I calculate phi of Z? Yeah. Exactly. It's the integral of this function, right? Because whenever I say probability of Z less than Z, that means that integral of f of x, p of x from -infinity to Z, right? Any questions? So any ideas how we can calculate that integral? So how can we calculate this integral? Any suggestions? From -infinity to Z, and my f of x is 1 over square root of 2 pi sigma e to the minus x minus mean. So x minus mean to the power 2 divided by 2 sigma squared, right? So this is my f of x. And it's in fact simpler than this because my sigma is 1. So I can simply plug in 1 here. And my mu is also 0, right? Because whenever I write Z, I mean that mu is 0 and sigma squared is 1. I think somebody on the Zoom is not muted. Please, if you are not asking question, mute yourself. It's basically the bounds are from minus infinity to z. So what is the question? Yeah, I mean the function is going to go to 0, but still we need to integrate from minus infinity, because this function, remember previously we changed the bounds because the function was 0 sometimes, right? Here we can't change the bound because this function f of x is never exactly 0. You're right, it does go to 0 in the limit, but that doesn't mean that, you know, we can change this bound. Let me find out who's so please mute yourself. I can hear somebody breathing on the Zoom. Can you please mute yourself? Okay, thank you. Okay. Any ideas how we can calculate that integral? So I meant
could we?
Yeah, go ahead.
Sorry, I didn't mean to cut you. Could we do the integral instead of z to infinity with the bounds and then subtract that from 1?
No, sorry, that was so this was a trick question. In fact, it's impossible to do that integral, right? So mathematicians early on proved that. So it is very interesting that people actually did prove for a long time. People were trying to calculate the integral, and then you know, I think a long time ago, 70 years ago, there are proofs that it's impossible to do the integral in closed form, right? So that means that we need a computer to do the integral, right? So that's the only bad property of the Gaussian distribution. It means that you can't really integrate it from, you know, minus infinity to any number in closed form, right? So what should we do? Yeah, we use a computer, or like in the exam, we don't have a computer, so we use a table, right? So this table is part of the crib sheet, right? So this appendix 3 in the crib sheet provides the integral of this function from minus infinity to any number, right? So you don't need to integrate it by hand. You can simply use the table, and we will do that. Don't worry, you will see how we use this table. Any questions? Yeah. Yeah, so this function has some nice properties, right? So for example, you are right. The integral from, so the first property is that it's symmetric, right? So we will come to that a lot. We will actually use that a lot in this course, that this distribution is symmetric. It makes our life very easy, right? So that means that the integral from minus infinity to any z, so let's say this z, is equal to the integral from plus infinity to, you know, minus z, right? But still, these tricks will not help us calculate the integral from minus infinity to z, right? I mean, we know that they are equal, but we don't know. The only thing that we can calculate, and this one's actually, if instead of z you plug in 0, it's easy to prove that the integral is, does anybody know what's the integral of, what is phi of, exactly, phi of 0 is 0.5. What's your name? Xian? Yeah. So phi of 0 is 0.5, right? And that's, you can look at the table, and the other reason is that I just said the distribution is symmetric. So that means that this part is equal to this part, and they should add up to 1. So each one of them is half, right? Okay. So let's look at the first question. Assume z is a standard normal random variable. So once I say standard normal, by standard I mean mu is 0 and sigma squared is 1. And by normal I mean it's a Gaussian function, right? And the goal is to find probability of z less than 1.5, right? So I encourage you to always plot the Gaussian distribution. It really helps you basically visualize the problem, right? And avoid, stupid mistakes. So the question says standard normal. So immediately we can draw a normal distribution with a mean of 0. There's no way to draw the variance, right? So you just draw some bell-shaped curve, right? So I can't really show that the function that I just drew has a variance of 1, right? But we can always draw the mean, right? So this is the mean. And I want phi of z less than 1.5. So this is 1.5. Right? So the only thing I can say is that the probability should be more than 0.5, right? Because I'm interested in this area, and the probability of this area for sure is more than half, right? So I look at the table. So in the table, I look at row 1.5, right? And so basically, this is the columns provide one decimal point, and then the rows provide additional decimal points, right? So I want exactly 1.500. So the probability is this number, 1.500 is 0.933, right? So very high probability. So for example, if I wanted a probability of z less than 1.52, what would be the number? Yeah, exactly, 0.9357. Yep. Yeah. So yeah, I basically cropped a lot of values. The table is huge. Yeah. Any other questions? Okay. Okay. So yeah, we just calculated this one. And if I want to calculate the probability of z less than 0.02, 0.02 is for row 0, so 0.02, and that's the probability, right? We can see that it's very close to 0.5, right? It's 0.507, quite close to 0.5. Any questions? Okay. All right. So you might ask, what's the use of this table? Because it's quite rare that, my distribution has a mean of 0, right? Like how many distributions do you know that have a mean of 0 and variance of 1? Not many, right? So one very, very nice property of the Gaussian function is that any Gaussian function can be converted to the standard form using this simple transformation, right? So no matter what your mu is and what your sigma is, using this simple linear transformation, you can convert any x into a standard case, right? So that's why this table is useful, right? Otherwise, we should have given you tables for different values of mu, different values of sigma, which is impossible to do, right? So the only table that you need is a table for sigma of 1 and mu of 0. Any other mu and sigma can be converted to the standard form using this simple equation, right? So I do highly encourage you to memorize this equation, because for the rest of this course, we constantly use this equation in many, many different chapters, right? So, and it's a simple equation. Whatever random variable you have, you subtract the mean and you divide it by the standard deviation, right? And this is also a very common step in my own field, is deep learning. So at the beginning, whatever random variable we have, first we subtract the mean and then we divide by the standard deviation. That makes things a lot easier to work with, right? And if you worked in signal processing, you know that we call this whitening a signal, right? When you remove the mean and then divide by the standard deviation, the signal becomes a white signal, right? That means that all the frequencies are, it basically has a zero mean and unit variance. So in this case, the expected value is 0 because the mean is 0 and the variance is 1, right? And again, you for whatever random variable x that you have, which is not standard, you can use table tree to find the probabilities, right? So don't worry if you're confused. It will become very clear with just one example. Right? So suppose that I have a current that's a normal distribution with a mean of 10 and standard deviation of 2. Right? So I know that my average current is 10 and its standard deviation is 2. What's the probability that the current is between 9 and 11? Right? So again, we draw the distribution. So the distribution is a normal distribution with a mean of 10. And I want the probability that my current is between 9 and 11, right? So I want this area under the curve. Any questions so far? Okay, so basically what I'm interested in is probability that x is between 9 and 11, right? So in the picture that I drew, this axis is x, right? And this curve is f of x, PDF of x, right? So basically what we have to do is we have to use this equation. Z is equal to x minus mean divided by sigma, right? So do memorize this equation because it's very useful for the entire course. Yeah.
Or like any, like, how do you know if something falls that you could like plot all the points, short of doing that?
Yeah. So that's a very good question. So the question is, how do we know a distribution is Gaussian or not, right? Before doing the experiment, for example, I mentioned that the number of radioactive particles that pass through any unit area or any area is a Poisson distribution, right? Why not a normal distribution, right? So yeah, one solution is to plot it, like do experiments, plot it. So in this course, we don't talk about it, but there are techniques called goodness of fit, right? So you see how good your distribution fits to the Gaussian curve. And then there are like mathematical tests that you do to find out whether a distribution is Gaussian or not. But you can also use theory, right? So you can say that I had no idea what my original distribution was, but I repeated my experiment 40 times and I averaged the result, right? So since I repeated the experiment 40 times and I averaged the result, no matter what the original distribution was, my final distribution is Gaussian because of the central limit theorem, which we will study later on. So any experiment that is repeated many times, the average value becomes a Gaussian distribution. And there's proof for that. Okay, so we have to follow basically this equation to make it standard. So we basically apply, we subtract mu and divide by sigma in all three sides of basically this inequality. So 9 minus 10, because my mean is 10, divided by 2, because my sigma is 2, and then x minus 10 divided by 2, and then 11 minus 10 divided by 2. And here see that x minus mean divided by 2 is z. So I replace that with z, right? And then I compute these two values. So this line corresponds to this curve, and then this line here corresponds to this other curve. So if this is my z, what is the mean value here? Exactly, it's 0. And I want the probability that my z is between minus 0.5 to 0.5. So basically I want this area, right? So this line corresponds to this curve. And then what I can do is that, to find this area from the table, what I will do is that I will say this area is equal to, so basically the purple area is equal to minus 0.5 and then 0.5 is equal to red area, sorry, green area minus yellow area, right? So this minus this is equal to this, right? And the reason I have to do this basically trick is that the table doesn't give me, this table tree doesn't give me the probability between number A and B. All it gives me is probability from minus infinity to some number, right? So to find probability between two numbers, you calculate the probability until the second number, and then you subtract the probability until the first number from that, right? So this area minus this area is equal to this area, and that's how we use the table. Yeah. So the question is there an easier way to calculate? Yeah, let's first make sure everybody understands this, and then I was actually thinking about that also, if there is another way to calculate this area.
Sir, I have a question.
Yeah, go ahead.
I was wondering why the probability here is less than 0.6, because didn't we say that for any normal random variable distribution, if it's between plus minus of sigma, it should be 68%? And this is indeed between plus and minus sigma.
Yeah, so that's an excellent question. So anybody knows the answer? So the question is, remember early on when we introduced the Gaussian distribution, I mentioned that the probability of the random variable being between mu minus sigma to mu plus sigma was 68%, right? It's very, very first curve that I showed you, right? 68%. So why here I have 38%? Yeah.
It's not plus and minus sigma. It's like half.
Exactly. Yeah. What's your name? Jan? Yeah. So that's correct. Here it's not plus minus sigma, it's plus minus half of sigma, right? So 0.5 means half of the sigma, right? Because in this distribution, sigma is 1. It's the standard case, right? So because it's half of sigma, my probability is around 0.4, much less than 0.6. Did I answer the question?
Yes, sir. Yes, sir. Thank you so much.
Yeah, sure. So now let's look at the other question. So what was your suggestion to calculate this probability? Yeah, go ahead.
You can just look at the table for the bigger number.
For
0.5.
okay, so that is 0.3. So this area is 0.3. So let me write it down.
0.6914.
Oh, 0.5, sorry. Yeah, so let me write it down. So this area is 0.308. And then this area in green, that is 0.69.
And then you can just take away the z of 0, which is half, and then just double
Yeah.
again because it's symmetrical. So
Yeah, you can do that. Yeah. So the other solution that was proposed was let me let's make all the writing go away. So basically, the other solution is to do the following. I think the one that I wrote is simpler, but let's write this one down also, because I think it's interesting. So the other solution is we want the probability between minus 0.5 and 0.5, right? So you calculate basically this probability, that is 0.308, right? And then you subtract, so we know that up to here, which is 0, this probability is half. So this area here, this other area, is going to be 0.5 minus 0.308, right? And then we know that this area and this area are equal. So the answer is 2 times this number. Was that your suggestion? Yeah, that's correct.
well, but that only works if you have the Z between two numbers that are identical. It won't work if the number on the left isn't identical to the number.
Exactly, yeah. So this solution, the other alternative solution that was, what's your name? Ali. So the alternative solution that was proposed by Ali only works if this bound from A to B is a symmetric bound, you know, from minus some number to plus some number. It doesn't work if these two numbers were not equal, right? So, but the other solution here always works from any A to any B. Any other questions? Okay, so let's move on. So basically, graphically, this is what's happening. So when I have this distribution that has a mean of 10 and a standard deviation of 2, when I convert it to, so this is a normal distribution, also known as Gaussian distribution. When I convert it to a normal distribution, the mean becomes 0, so mu becomes 0. And then, for example, number 4 here gets converted to number -3. Why is that? Because of this transformation, right? So if I plug in 4 into this function, this becomes 4 minus 10 divided by 2, and that is -3, right? So that means that number 4 here, 4 moves to number 3 here, right? So it's a linear transformation. All numbers here move to new numbers. 6 moves to -2, 8 moves to -1, and so forth. And 10 moves to 0. Any questions? Okay. So one very common mistake in the exams is that students get the wrong number from negative Z, right? So negative Z is a little bit, so the table, you know, is a little bit misleading because the first row is not 3.9. The first row is 3.99, right? So always pay attention to that. It's the last row is 3.9. It's exactly the opposite of positive numbers, right? In the positive numbers, the first column. In the positive numbers, the first column basically is exactly this number. So the decimal points were 0 for the first number. But here for the first number, the decimal is actually the maximum, right? So if I show you some numbers, this number, for example, 0.0013, that's the probability of Z less than -3, right? So if you want to calculate probability of Z less than -3, you shouldn't look at the first column. You should look at the last column, right? Similarly, if you want the probability of like Z less than -3.2, you shouldn't look at the first column. You should look at the last column, right? And the reason for that is that, you know, it's these numbers are increasing. So that's why they had to write it like this, you know. So like, for example, this number, 0.0048, the next number after this is this guy here. So it is actually a continuous function. So they had no choice. I mean, for negative numbers, we have to write it like this. Any questions? Okay. So now this question is a little bit different from the previous one that we calculated. So here we know that my current is normally distributed with a mean of 10 and standard deviation of 2, right? And here I'm not asking you what's the probability that the current is between these two values. Here I'm asking the value for which the probability that the current measurement is below this value is 0.98, right? So basically always drawing the distribution is a very good idea. So I have a distribution, a Gaussian distribution with a mean of 10 and standard deviation of 2, and determine the value for which the probability that the current measurement is below this value is 0.98, right? So I want to find some value, right, x, such that the probability that I'm below this value, this area under the curve, is 0.98, right? So the question is, you know, let's say, you know, like the specifications of some wire do not allow the power, you know, like we want to find the maximum current that I can have, you know, with a probability of 0.98, right? With a very high probability, right? So basically, again, we should use this equation, which should become your friend. Z is equal to x minus mu divided by sigma, right? So the first thing we do is that we make it standard. So x minus mu divided by 2. So so now this becomes my Z, right? Using this equation, this is Z. And I want this to be 0.98, right? So I go look at the table and I find the value which gives me 0.98, right? So that means that so here in this picture that I drew, this was my X, random variable X. In the new picture that I'm drawing, this is my Z, which means that it's the standard case. This is 0. So I want some Z such that this area is 0.98, right? So I look at the table and I find out that Z is equal to 2.05, right? So my Z is 2.05, and then I know my Z. So I know X, I know mu, and I know sigma, so I can simply calculate X from this equation, right? So my X becomes 14.1. So this X here is 14.1 milliamps. Any questions? Yeah. Oh, okay. So basically, my X is a normal distribution, but it's not a standard normal because the mean is, you know, non-zero, right? So what I do is that whenever you see that either the mean is non-zero or standard deviation is not 1, right? Either one of these, right? It doesn't mean like you don't need both of them to be, you know, other values. Even if one of them is, even if mean is not 0 or standard deviation is not 1, sorry, you must use this equation, right? So because of that, I have to use this equation. So I have to subtract the mean and then divide by the standard deviation so that this new random variable becomes the standard case. That's why. Yeah. Any other questions? Okay. I think this is the last slide that I wanted to cover. Yeah. Let's see if yeah, so let's stop here.